Good morning, all of you. Welcome to Sri Jay in the Time Zone. So far, we have completed in lecture 1 some general properties of D block elements, D and F block elements, mainly D block elements we are doing now. Next, we are going to discuss more about D and F block elements in this lecture, that is general properties. Listen carefully and follow the instructions. So, in this lecture, we are going to discuss some more properties of D block elements because all the general properties of D block elements has not yet finished. So we are going to discuss some more properties of D block elements in this lecture. So let us start now. The relative stabilities of various oxidation states of D and F block elements, mainly D block elements we are discussing now. The metal in higher oxidation states. Yesterday we have means in the previous lecture we have done about oxidation states. So they are showing variable oxidation states because of the availability of D electrons. So the metal in the higher oxidation states only form fluorides. So like manganese fluoride, as it is most electronegative element. And these fluorides are mainly ionic in nature. Very important point. Actually, the metal oxides means the metals in the higher oxidation states will form covalent compounds. But only with fluorides they'll form ionic in nature. Means manganese fluoride, MnF7, for example. So the oxygen state of manganese is +7, but still it is ionic in nature because fluorine is most electronegative element. The chlorides, bromides, and iodides have ionic as well as covalent character. They have ionic character as well as covalent character, like MnCl4, manganese tetrachloride, manganese tetrabromide, and so on. They form ionic as well as covalent character. Lower oxygen states, ionic compounds, and higher oxygen states, covalent compounds. Halides of metal in higher oxygen states are relatively unstable and undergo hydrolysis very easily. So, example here, titanium chloride, that is titanium tetrachloride, on hydrolysis forms titanium dioxide along with HCl. So, the metals in the higher oxygen states, like in this titanium is the +4 oxygen state. The oxygen state of titanium is +4. So, not only manganese, we can say about titanium, scandium, vanadium, etc. Halides of metal in higher oxygen states are relatively unstable and undergo hydrolysis very easily, and they form their respective oxides. The solutions of several halides are acidic in nature due to hydrolysis, as they are covalent in nature and they form acidic. So the solutions of several halides are acidic in nature because they are able to give acids. Continuation. The highest oxidation number are shown in titanium tetrachloride, bromide iodide, vanadium pentafluoride, and chromium hexafluoride. The +7 state for manganese is not represented in simple halides, and beyond no metal has a trihalide except FeX3 and COF3. So the highest trihalide is after iron, we have only FeCl3, COCl3, and so on, cobalt trichloride, cobalt trifluoride, etc. And all Cu plus 2 halides are known except iodide. So copper iodide is not known, but copper chloride, copper bromide, and copper fluoride is known. In this case, copper +2 oxidizes iodine -2 iodine. So here copper +2 ions iodizes, oxidizes iodine -2 iodine. It displaces iodine. Many copper 1 compounds, copper 1 means copper in +1 state, are unstable in aqueous solution and undergo disproportionation. Disproportionation means here copper +1 state, here +2, and here it is 0. So one it is increasing, another it is decreasing. So same element is undergoing oxidation as well as reduction. Hence, it is called as disproportionation reaction. The oxygen state of copper in this is +1, in this it is +2, and in this it is +0. So many copper 1 compounds are unstable. So copper is more stable in +2 state only. Copper is more stable in +2 state. It is less stable in +1 state. Less stable. So all these points are important for entrance exams. Please note down all these points in your classwork. The stability of plus 2 rather than Cu plus is due to much more negative hydration enthalpy of Cu plus 2 than that of Cu plus. So it is due to hydration enthalpy, which is more than compensates for second ionization enthalpy of copper. So why Cu plus 2 is more stable than Cu plus? Because of negative hydration enthalpy of Cu plus 2 than that of Cu plus 1. The elements of first transition series. Now we are going to discuss about oxides, which is very, very important. Oxides of transition metals are important. The elements of first transition series, that is 3D series, form a number of oxides. That is, they form oxides of type MO, M2O3, M3O4, MO2, M2O5, and MO3. These oxides exhibit acidic, basic, and amphoteric behavior. Very, very important. All the types of oxides are forming. They can form acidic oxides, basic oxides, and amphoteric behavior. The highest oxidation number in the oxides coincides group with the group number and is attained scandium tetroxide, that is discandium trioxide to Mn2O7. Besides the oxides, oxocations stabilize V plus 5, VO plus 2, V plus 6 as VO plus 2, and Ti plus 4 as TiO plus 2. So, oxocations also will form, besides the oxides, they form oxocations. And about the nature of oxides, they can form acidic oxides, basic oxides, and amphoteric oxides. Acidic oxides usually higher oxygen state. So higher oxides, higher oxidation number oxides are acidic in nature, and lower oxidation number oxides basic in nature, and they are acidic as well as covalent. Also, we can write covalent in nature. Whereas lower oxygen states, oxidation oxides, they are basic in nature. They form ionic in nature because oxygen is electronegative. Continuation now. So you can see the nature of oxides. The ability of oxygen to stabilize these high oxygen states exceeds that of fluorine. Thus, the highest manganese fluoride is Mn4 only, whereas highest oxide of manganese is Mn2O7. In MnF4, it is plus 4 state, and in Mn2O7, it is plus 7 state. So manganese is plus 7 state in this, and manganese is plus 4 state in this. So what is the point here? The ability of oxygen to stabilize these high oxidation states exceeds that of fluorine. So manganese can form with fluorine with only four fluorine atoms, whereas manganese can form with 7 oxygen atoms. So the ability of oxygen to form multiple bonds to metals explains its superiority. In the covalent oxide Mn2O7, as I told you, it is covalent in nature. Each is tetrahedrally surrounded by oxygen atoms, including manganese O, manganese bridge also. So they form tetrahedral shape. Continuation. You can see different here. This is very, very important because they'll ask which of the following is acidic, which of the following is basic, which of the following is amphoteric. So basically titanium forms 3 types of oxides: titanium dichloride, titanium trichloride, titanium, 3 types of halides, titanium tetrachloride. Similarly, vanadium, VCl2, VCl3, VCl4, and VOCl3 also. Now, the ionic character, it is vanadium, titanium chloride. In the lower oxygen state, they form ionic compounds and they are basic in nature. Very, very important. The metals in their lower oxygen states are ionic in nature. The compounds are ionic in nature and they are basic also. And the metals in their next have a medium oxidation number, that is plus 3. It is formed less ionic and they are amphoteric. Very, very important. They are amphoteric in nature. And the metals in higher oxygen state, they are covalent and acidic in nature. They are called strong Lewis acids. So this is the trend of metals with respect to halides. Now with respect to oxides also, you can see here all the metals are in plus 2 state. That is plus 2. All the metals are in plus 2 state. They are ionic and basic. So they form ionic compounds. So titanium oxide is ionic. Vanadium oxide is ionic. Chromium oxide is ionic. Manganese oxide is also ionic. Whereas if you see for titanium dioxide, that is tritanium trioxide, V2O3, Cr2O3, Mn2O3, the oxygen state of titanium is here, it is plus 4. Vanadium, it is plus 4. Again, we can say chromium, dichromium 2, this is also plus 4. and all the oxygen states with plus 4 oxygen state. With the metals with plus 4 oxidation number along with their oxides, they are less ionic and amphoteric. And with plus 4 again here also. Titanium dioxide, that is plus 4 oxygen state, and manganese dioxide also plus 4 oxidation state. Plus 4 and plus 4. Whereas V2O5, CrO3, MnO3, Mn2O7. These are the oxygen states with the maximum oxygen states. Vanadium plus 5 state, and chromium is plus 6. Manganese is also plus 6, and manganese plus 7 here. So their oxides are acidic and covalent. So which will form basic oxides, which will form amphoteric oxides, which will form acidic oxides. So all the three are important. So which are the following are amphoteric in nature? The metals in the oxidation number, higher oxidation number, that is plus 4 and plus 5, they are said to be amphoteric. And the metals with plus 2 oxygen state, they are said to be basic. And the metals with plus 6 oxygen state in their oxides, they are said to be acidic and covalent in nature. So this is very, very clear, very, very important. This. So by this, what you can understand, the metals in their lower oxygen states, the metals in their lower oxygen states are ionic. They form ionic compound and they are basic in nature. And the metals in the middle oxygen state, that is plus 4, plus 4, plus 4, plus 4, and plus 4, they are less ionic and amphoteric in nature. And the metals in their higher oxygen state in their respective oxides, that is CrO3, Cr2O7, Cr2O7 also will come into this category. Cr2O7 also will come into this category. Cr2O7 2 minus. So that is potassium dichromate. So they are acidic in nature and they are covalent. They form covalent compound. So all these points are very, very important. So please note down, because from this they will frame a question. Which are the following are acidic oxides? Which are the following are basic oxides? Which are the following are amphoteric oxides? So amphoteric oxides, Mn2O3, MnO2, V2O3, Cr2O3, Ti2O3, and TiO2. Basic oxides. Basic oxides means they form only with plus 2 state. So that is titanium oxide, vanadium oxide, chromium oxide, manganese oxide. And plus 6, that is chromium trioxide, manganese trioxide, dimanganese heptoxide, that is Mn2O7. They are in the higher oxygen state, the metals in their higher oxidation states. So as they are in higher oxygen states, they form acidic oxides and they are covalent in nature. So this slide is very, very important. Please note down in your classwork. Next continuation. Color of compounds. So already we have seen in the general properties, transition metal compounds exhibit color because of their unpaired electrons. Transition metal ions exhibit color in solid as well as in solution due to internal DD transition. Why they are exhibiting color? Due to internal DD transition, DD electrons transition. So the degeneracy of 5d orbitals is lost in the presence of magnetic field of ligands and electronic transition T to G to EG lie in visible region. So this reason also they lost. The metallic compounds, the transition metallic compounds exhibit color due to the metallic the transition metal compounds exhibit color due to DD transition, due to internal DD transition. We can say internal DD transition. This reason is very important. Definitely they'll ask the question based on this concept in the entrance exam. So the transition metal ions exhibit color in solid as well as in solution state due to internal DD transition. The degeneracy of 5d orbitals. Degeneracy means degenerate orbitals, means orbitals with equal energy. So what are degenerate orbitals? Degenerate means degenerate orbitals. Degenerate orbitals means same energy. Same energy orbitals. Already we know d orbital can form dx square, dxy, dyz, dxz or dzx, dx square minus y square, and dz square. These are the 5 orbitals. They'll form 5d orbitals. So this is 5d orbitals we have. So 1, 2, 3, 4, 5. So maximum they can take up to 10 electrons. This already we know. And these orbitals are called as degenerate orbitals. These are called what? Degenerate orbitals, because they are nothing but orbitals are having same energy. So these dxy is similar to dyz. The energy of dxy, dyz, all the energies are similar. So that's why these are commonly called as degenerate orbitals. These are called as degenerate orbitals. So the degeneracy of 5D orbitals is lost in the presence of magnetic field of ligands and electronic transition T2G to EG. Means electron will go from this orbital to this. So lie in the visible region. Visible region means they exhibit colors. The color observed corresponds to the complementary color of light observed. How the color will be given, because all these are formed in visible region of the spectrum. So the color observed corresponds to the complementary color of light absorbed. So based on the light, they give the color. So most of the metallic compounds are colored due to internal DD transition. The color of transition metal complex depends upon the magnitude. This is also important. This also they'll ask in the reasoning type question. Reasoning type. The color of transition metal complex depends upon the magnitude of energy difference delta naught between the 2D orbital 2D levels, that is T2G and EG. This we'll discuss in CFSC, that is crystal field splitting energy. Crystal field splitting energy. Crystal field splitting energy in coordination compounds. So the magnitude of energy difference delta naught between the two DA levels T2G and EG. And second point, an increase in the magnitude of delta naught decreases the wavelength of the light absorbed by the complexes. So delta naught is proportional to 1 by lambda absorbed. So these are the two factors where the color of transition metal depends. With decrease in the lambda, the color of the complex changes from red to violet. Because they are formed in the visible region, the color of the transition metal changes from red color to violet color. KMnO4 example, you can have potassium permanganate, that is KMnO4, potassium permanganate, potassium dichromate having D0 configuration, but they are colored due to charge transfer spectrum. In this, manganese is D0 combination because manganese is +7 state, all the 7 electrons are removed, and in this +7 state, all the 6 electrons are removed, +6 electrons. So they have, even though they are having D0 configuration, they do not have unpaired electrons, but still they are colored due to charge transfer spectrum. Very, very important. They are colored due to charge transfer spectrum. So the oxygen state of manganese is +7. +7 means in this case it is D0. And oxygen state of chromium is +6. +6 means all the 6 electrons of chromium are removed. So they do not have any electrons in D as well as in S. So even though they have D0 configuration and they have no unpaired electrons, even though they do not have unpaired electrons, but two these two compounds, that is potassium permanganate and potassium dichromate, exhibit colors due to charge transfer spectrum. Charge transfer spectrum, very, very important. This reason they will ask in the examination. Even though there is no unpaired electrons in potassium permanganate and potassium dichromate for chromium and manganese, but still they are exhibiting colors because of charge transfer spectrum. Because of charge transfer spectrum. This point is very important. Please note down in your classworks and remember this. Definitely they are going to ask in the examination. So please remember this point. Continuation. So scandium +3, titanium +4, and zinc +2 ions are colorless because they do not have unpaired electrons. Due to the absence of unpaired electrons. If you remove 3 electrons from scandium, it becomes argon configuration, inert gas configuration. If you remove 4 electrons from titanium, it becomes what configuration? Again, argon configuration. If you remove 2 electrons from zinc, so zinc, what is the atomic number? Zinc is 30. So zinc is what? You can have the configuration is 3d10 4s2. 3d10 4s2. After removing these 3 electrons, it becomes 3d10. Means no unpaired electrons. All are paired. As all the electrons are paired, so they do not exhibit color. So scandium +3, titanium +4, and zinc +2 ions are colorless due to absence of unpaired electrons. Cu +2, it has one unpaired electron because copper is what? Copper configuration is 3d9. and 4s1. So 3d10, sorry, it is 3d10 4s1 unusual configuration. If you remove two electrons, it becomes what? Copper 2 plus becomes 3d9. 3d9. It has one unpaired electron. So due to this unpaired electron, it exhibits blue color. Na plus 2, it has unpaired electrons, green color. Cobalt plus 3, blue color. Iron plus 2, green color. Manganese plus 2, pink color. Chromium plus 3, violet color. Titanium plus 3, purple color. So above all are colored due to DD transition. They are colored due to DD transition. This they will definitely ask in the examination. But MnO4 minus Cr2O7 minus Cr2O7 2 minus and Cr4 minus are colored due to charge transfer phenomenon, which we have discussed in the previous slide only. Even though they contains 0 electrons in d orbitals, here d0, here also d0, and here also d0, means even though they do not contain unpaired electrons, but still yet they are colored due to charge transfer phenomenon. And why these elements are colored? Due to dd transition. And moreover, Cu plus is colorless. Why? Because it has no unpaired electron. Cu plus is colorless because it have Cu plus configuration is 3d10. 4s1 will go off, so only 3d10. So all the electrons are paired, so that's why Cu plus is colorless. So these are the colors exhibited by the elements, by the metal ions. Very, very important. Scandium plus 3, titanium plus 4, Zn plus 2 ions are colorless due to absence of unpaired electrons. So if they ask the question, which are the following are expected to be colored, then we have to search for unpaired electrons. If all are do not have unpaired electrons, then we have to search for the compounds in which manganese, manganate ion, chromium oxide ion, and chromium oxide ions. So these are, even though they do not have unpaired electrons, these are expected to be colored due to charge transfer phenomenon. So either this they'll ask or this they'll ask, but they will not ask the color, particularly the color of Cu plus 2 ions is Nickel plus 2 ions is cobalt plus 2 ions. So I don't think you have to remember these colors, but you should remember whether they are colored or not colored. That is, we can say easily by the number of unpaired electrons. If a metal ion is having unpaired electrons, it exhibits color. If a metal ion do not have unpaired electrons, it will not exhibit color. And the metal ion which do not have unpaired electrons, yet still exhibits color, that is only manganate ion, chromium oxide ion, and chromium oxide ion. So Cr2O7 dichromate ion and permanganate ion and chromate ion, CrO4 2 minus. So dichromate, chromate, and permanganate ions only exhibit color due to charge transfer phenomenon, even though they do not contain unpaired electrons. Even though they do not contain unpaired electrons, but still these three are exhibiting colors. Very, very important. So please note it down. And if they are colored, they should have definitely unpaired electrons. In all these elements, we have unpaired electrons. In all these ions, we have unpaired electrons. That's why they are exhibiting color. You can see the configuration of these. So after losing two electrons, copper becomes 3d9. Cu plus 2 becomes 3d9, means it has one unpaired electron. Like that, Fe plus 2, it will become 3d4. So like that, you will have definitely color. They exhibit colors. They exhibit colors. So the metal ions which have unpaired electrons exhibit colors. The metal ions which do not have unpaired electrons exhibit no color. And the metal ions which do not have unpaired electrons but still exhibit colors are manganate ion, dichromate ion, and chromate ion. So these are the three exceptions we have. And the why these unpaired electrons, metal ions exhibit colors due to DD transition. Due to DD transition. This reason is also important. So the unpaired electrons, the metal ions having unpaired electrons exhibit colors due to DD transition, internal DD transition. And the metal ions which do not exhibit color due to the absence of unpaired electrons. Due to the absence of unpaired electrons. So these points are very, very important. So color of compounds is most important. Definitely they'll ask the question from this concept. So please note down all these slides. This total slide is very, very important. And what we have discussed so far in these 2 points are important. 3 points firstly. Point number 1, the metal ions which do not have unpaired electrons are colorless. Second point number 2, the metal ions which have unpaired electrons exhibit color. Example, copper plus 2 blue color nickel plus to green color, cobalt plus the blue, Fe plus to green color, manganese plus to pink color, chromium plus the aqueous violet color, titanium plus the aqueous purple color. So the metal ions which have unpaired electrons definitely exhibit colors. That is point number two. And these colors are due to, they exhibit colors due to the presence of unpaired electrons. No, it is not due to the presence of unpaired electrons, but due to internal DD transition. Compulsory means here they should have unpaired electrons, then only they can exhibit colors. But the reason for exhibiting color is due to DD transition, due to internal DD transition. And the metal ions which do not have unpaired electrons but still they exhibit colors are the exceptional. That is point number four. That is due to charge transfer phenomenon. And that point, those metal ions are nothing but manganese oxide, that is permanganate ion, that is manganate ion, dichromate ion, and chromate ion. So these, in these ions, the metals have no unpaired electrons because they have D0 configuration. They do not have any unpaired electrons, but yet still they are producing color because of charge transfer phenomenon. Charge transfer phenomenon. So all these 4 points are very important in this. We have 4 points we have discussed clearly. So please note it down in your classwork and remember this for the entrance exam. Next, magnetic properties. As they have unpaired electrons, they are said to, generally we have two types of magnetic, mainly diamagnetism and paramagnetism, and few are attracted by strongly, very strongly they are said to be ferromagnetic. So when a magnetic field is applied, when a magnetic field is applied to substances, mainly two types of magnetic behavior are observed. One is diamagnetism and there is paramagnetism. What are diamagnetic substances? Diamagnetic substances are repelled by the applied field, while paramagnetic substances are attracted by the magnetic field. So these they will repel each other from the, if you apply magnetic field to a diamagnetic substance, it repels. Whereas for paramagnetic substance, they will attract. Few are attracted very strongly by the means of magnetic field and they are said to be ferromagnetic. Example, iron. Iron, nickel, cobalt are ferromagnetic in this group. So what are diamagnetic and what are paramagnetic substances? Let us see now. So simple it is. Paramagnetism arises due to the presence of unpaired electrons. So if you know electronic configuration, it is very, very important electronic configuration. From that electronic configuration, they can, based on the electronic configuration, they can form easily 4 to 5 questions. That is question number one, whether it is paramagnetic in nature or not. Question number two, whether it is exhibiting color or not. Question number three, the magnetic moment, how to calculate magnetic moment. Question number four, question number three, whether it is means the magnetic moment of the substance. Question number four, so they'll ask you about acidic nature, amphoteric nature, or basic nature. So like this, they can ask n number of questions based on electronic configuration. So the main basis for all these questions is electronic configuration. If you don't know electronic configuration of 3D, 4D series, you are unable to answer these questions. That's why electronic configuration of D and F block are very, very important. Electronic configuration of D and F block elements are very, very important. They are very much important because from these electron main basis of electron configuration, we can find oxygen states. If you find oxygen states, automatically we can find unpaired electrons and we can find paramagnetic nature, diamagnetic nature, acidic nature, or basic nature, covalent compound, ionic compound, as well as magnetic moment. Finally, we have magnetic moment. So almost 6 to 7 questions will be framed based on this. 6 to 7 questions. So that's why the main basis for answering all these 6 to 7 questions is based on electronic configuration. Until and unless if you don't know the electronic configuration of D and F block elements, it is very difficult to solve these questions. So please remember mainly D and F block elements electronic configuration compulsorily. If you don't know electronic configuration of D and F block, you are unable to find 4 to 5 questions, 6 to 7 questions compulsorily. And these 6 to 7 questions definitely they are going to give in the entrance exams. So what are the different questions based on this? I have discussed already with you. If possible, I'll write in the next slide. So now coming to magnetic properties of magnetic properties, paramagnetism. How can we say it is paramagnetic in nature? A substance is paramagnetic in nature if it contains unpaired electrons. So paramagnetism arises due to the presence of unpaired electrons, each such electron having a magnetic moment associated with its spin angular momentum, that is S, and orbital angular momentum, that is L. So for 3D series, L is negligible. Spin only magnetic moment is possible. So mu of spin is equal to root of n into n plus 2 Bohr magneton. This is the unit of magnetic moment, Bohr magneton. So root of where n is called number of unpaired electrons. For example, what is the spin only magnetic moment of Fe plus 2 ion? Let us see now. Fe plus 2 ion, it is equal to. So first spin only magnetic moment of Fe plus 2 ion. First we have to consider Fe ion atomic number is 26. So its configuration is argon 18, 3D 4, 5. So 18 and here it is 8. So 3d6, 4s2. 3d6, 4s2. So if two electrons are removed, then it becomes Fe plus 2. So Fe plus 2 configuration is argon 3d6 only. 3d6 means it has how many unpaired electrons? You can see here. You can see here 3d6. First electron, second electron, third electron, fourth electron, fifth electron. Fifth electron will go like this, and sixth electron will start pairing. So it has how many unpaired? 1, 2, 3, 4 unpaired. It has 4 unpaired electrons. How many unpaired electrons? 4 unpaired electrons. So magnetic moment is equal to mu is equal to root of 4 into 4 plus 2. That is 4 plus 2, 6, 6, 4 is 24 equal to root of 24. It is almost equal to 5.98 Bohr magneton. Sorry, 4.98 Bohr magneton because 4, 4, 16. 5, 5 is 25. So it is 4.98 Bohr magneton. Anyway, we are going to do these numericals later on. So it is 4.98 Bohr magneton. So the main basis for this is electronic configuration. If you don't know electronic configuration, it's very difficult to find number of unpaired electrons. And a paramagnetism arises due to the presence of unpaired electrons, and mu spin only magnetic moment. That is, what is mu here? Magnetic moment. Magnetic moment is calculated by the formula mu is equal to root of n into n plus 2. However, these problems we have done in atomic structure in 11th class. If you don't remember, still you can do it here. So root of n into n plus 2, that is 4.98 Bohr magneton, where n is the number of unpaired electrons. One Bohr magneton is equal to EH by 4 pi mc. So how we got this Bohr magneton? It is equal to electron into Planck's constant, charge of electron into Planck's constant by mass of electron into velocity of electron, that is C. So EH by 4 pi mc. Even this formula also they can ask in the examination. So what do you understand by this? Paramagnetism arises due to the presence of unpaired electrons. Each such electron having a magnetic moment associated with its spin angular momentum and orbital angular momentum. For 3D series, L is negligible. So spin quantum only, spin magnetic moment only will be taken into consideration. So spin magnetic moment mu is equal to root of n into n plus 2, where n is called number of unpaired electrons. So if we don't know electronic configuration, it's very difficult to find number of unpaired electrons. So already pairing starts. In iron, we have 3d6. So 1, 2, 3, 4, 5 electrons are like this, and sixth electron will start pairing up with this. So this is paired already. So only how many unpaired? 1, 2, 3, and 4. So this we'll discuss later. Example I want to give, that's why I have given it. Next continuation. Next, you can see here number of unpaired electrons. Clearly they have mentioned. Scandium plus 3, 3D 0, no unpaired electron, that's why it is colorless. Magnetic moment is 0, magnetic moment observed is 0. And this is titanium plus 3, it has 1 electron in the d orbital. So it is a number of unpaired electrons is 1. It is 1.73. Observed magnetic moment is 1.75. Titanium plus 2, 3D2. So 2 electrons, 2.84. And 3 electrons, if they have 3 electrons, it is 3.87, because the formula is mu is equal to root of, how we got it is 3.87, because it is mu is equal to root of 3 into 3 plus 2. 3 into 3 plus 2. So for 3 electrons, I'm showing example. So 3 into 3 plus 2 is 3 plus 2, 5. 5 is a 15. Root 15 is nothing but How much it is equal to? It is exactly almost equal to 3.87 Bohr magneton. So next 3D4, as in the case of iron. So 4.90. Fe plus 2, 3D6, even though they have 6 electrons. From here, if you see, till here it is common, that is 5 electrons. But here 6th electron. How we got 4 electrons here? Because you can see here this diagram clearly so that you can understand it better. First electron, second electron will go, third electron will go like this, fourth electron will go like this, and fifth electron will go like this. Now, sixth electron will start pairing up. 6 means pair. So, total 6 electrons. So, in iron 3D6 we have. So, 6 electrons. Sixth electron is paired. So, now what are how many unpaired electrons? 1, 2, 3, 4. That's why it is 4 unpaired electrons. Suppose 7 electrons are there, means this also will get paired. So, it will have 3 unpaired electrons. That's why 3. And 8 electrons means it also will get paired. So, it is having 2 unpaired electrons. 9 electrons means this also will get paired. So it is having 1 unpaired electron. In the case of copper, you can see. And 10 unpaired electrons means no 10. 10 electrons means all are paired. So no unpaired electrons, so 0. So first it was starts with 0 to 5, then again 4 to 0. Remember this, very, very important. So this is called the electronic configurations of unpaired electrons of 3D series. 3D series. You have to remember even 4D also. They can ask from 4D or 3D. Anyway, 5D is not that much important because higher atomic numbers. So children may not be able to remember that much configuration. So that's why usually they'll touch 3D. If not, they'll go for 4D also. But mainly 3D. Compulsory you have to learn without fail 3D elements, the configuration, the atomic numbers. If you don't know the atomic numbers, it's very difficult to write the configuration. So scandium, it is 8, 19, so 21, titanium 22, like that you will get. So zinc, it is 30. So it starts with 21 to 30. And you have to remember the sequence. Chromium, it is 24, atomic number. Vanadium 23, titanium 20, titanium, chromium is 25. Manganese 25. No, somewhere we have missed it. Titanium 2 times they have given. That's why it is gone wrong. So this is 22, 23, 24. And manganese 25. Iron 26. Cobalt 27. Atomic numbers. Nickel 28. Copper 29. So 21 to 30. So this is 22 and 22 because the titanium plus 3, titanium plus 2. So all these elements which have unpaired electrons, they exhibit colors. So these exhibit colors because they have unpaired electrons. These are colored. So you know how to calculate magnetic moment. The formula is mu is equal to root of n into n plus 2. Mu is equal to root of n into n plus 2. And you know how the pairing takes place in d electrons. First 5 electrons will not get paired up. Sixth electron will start pairing. Seventh electron, eighth electron, ninth electron, 10th electron. Continuation. Formation of compounds, colored compounds, complex compounds. Next property, very important property is complex compounds. Due to the availability of d electrons, they form complex compounds. The transition metal ions forms a large number of complex compounds due to small size of the metal ions and their higher ionic charges and the availability of these reasons are very important. Why they are forming complex compounds? Due to small size of the metal ions, reason number 1. Second one, due to their high ionic charges, that is reason number 2. And third one, the availability of d orbitals for bond formation. This is third one. So basically, these based on three reasons only, they can form complex compounds. Example, you can see here potassium hexacyanoferrate. So this is potassium ferrocyanate. So it is nothing but complex name is hexacyano potassium ferrate. Ferrate 2. The oxygen state of iron is plus 2 here. And copper, it is plus 2 again because it is given already plus 2. So tetraamine copper, amine copper 2. The name of this compound is tetraamine copper 2. Like this we have hexacyano potassium hexacyano. potassium hexacyanoferrate 2, ferrate 2. So they form complex compounds due to mainly three reasons. What are those? First reason, due to small sizes of the metal ions. Second reason, due to their high ionic charges because of their oxidation states, because of their oxidation states. And third one, availability of d orbitals for bond formation. So basically, these three reasons will form, they will leads to the formation of complex compounds. So most of the transition metal forms complex compounds. Next continuation. As I already told you, most of the transition metals are used as catalysts. Why they are used as catalysts? Because they provide a clean surface for adsorption. Apart from that, we have one more reason also. So what is that reason? That transition metals and their compounds have catalytic property. This catalytic activity is due to availability to show variable valencies. Number one, availability of vacant d orbitals, ability to form unstable intermediate complexes, which weakens the bonds between the reacting molecules. And third point is large surface area available for adsorption. This we have discussed in surface chemistry, this point. So these are the 3 points which makes the transition metals used as catalysts. So these three reasons, these 3 points they'll ask in the examination, entrance exam, which are the following is true regarding transition metal catalysts. So they have the ability to show variable valencies, and they have the availability of vacant d orbitals and ability to form unstable intermediate complexes, which weakens the bonds between reacting molecules, and large surface area they provide large surface area available for adsorption. So these are the basic reasons for the transition metals used as catalysts. So since already we know nitrogen and hydrogen in the presence of iron forms ammonia gas in Haber's process. So we can use, so we have so many reactions in which transition metals are used as catalysts. Example, you can see iron 3 catalyzes the reaction between iodine and pus sulfate ion. So iodine ion combines with pus sulfate ion in the presence of iron 3 catalyst and form iodine and sulfate ion. An expression for this catalytic action can be given as, first what happens, Fe plus 3 ion combines with iodine plus 2 makes it iodine and Fe plus 2. So it is undergoing reduction and this is undergoing oxidation. So Fe plus 3 oxidizes iodine ion to iodine, and 2Fe plus 2 combines with S2O8 and becomes again 2Fe plus 3 because the catalyst will not be used up in the reaction. Only again it should form. So that's why again Fe plus 3 is formed and SO4 2. So based on iron Fe plus 3, we have the products that is iodine as well as sulfate ion. So as Fe plus 3 is helping to form convert iodine minus to iodine. So that's why it is used as catalyst. A catalyst is a substance which do not take part in the chemical reaction, but due to its presence, the reaction takes place faster. So what are the examples? Fe, Haber's process, nickel, hydrogenation process, the hydrogenation that is called production of vanaspati, and V2O5 vanadium pentoxide is used in contact process for the manufacture of sulfuric acid, and platinum it is used in Ostwald process for the manufacture of nitric acid. So all this we have discussed in P block elements, all these processes. So that's why they are used as catalysts. These are the examples. Next continuation. Very, very important. They have one more property. They can form, transition metal can form interstitial compounds. What are interstitial compounds? Interstitial compounds are those which are formed when small atoms like hydrogen, carbon, or nitrogen, very, very important, please note down. When small atoms like hydrogen, oxygen, carbon, or nitrogen are trapped inside the crystal lattice of metals. They are non-stoichiometric and are either neither ionic nor covalent. Because of the nature of their composition, these compounds are referred to as interstitial compounds. So, if the elements, small atoms like hydrogen, carbon, or nitrogen are getting trapped into the metallic kernels, into the metals, transition metal, crystal lattice of transition metals, they will form interstitial compounds. Examples for interstitial compounds. Now we are going to discuss. Please note down. So examples you can see here. For example, iron oxide. In this, Fe plus 2 is 0.95, they'll say. That is nothing but it has, in this, it has both Fe plus 2 as well as Fe plus 3. And Fe plus 2 percentage is 95%, and 5% is Fe plus 3 also. So that's why, as this element, this is called an interstitial compound. Interstitial compound. So the principal physical and chemical properties are they have high melting points than those of pure metals. So interstitial compounds have high melting points than those of pure metals. They are very hard. They retain metallic conductivity. They are chemically inert. So example, you can see titanium carbon, titanium hydrogen, Fe3H, VHO, 0.56 Mn4n. So these are all considered as interstitial compounds. Carbon, hydrogen, nitrogen mainly. In some oxides also like iron oxide. Next, very important property of transition metals, they can form alloys also. Alloy may be homogeneous solid solutions in which the atoms of the one metal are distributed randomly among the atoms of the other metal because of similar radii and other how can why they are forming alloys? Because of similar radii, atomic radii, due to lanthanide contraction and other characteristics of transition metals. Alloys are readily formed by these metals. So example like these alloys they'll ask composition. So composition of alloys is very, very important. So please note it down. Gather as much alloys as you can from all the books, whatever you have available, because they'll ask definitely the composition of alloys. For example, the composition of nichrome, it consisting of nickel, chromium, and iron. The composition of invar, it consisting of nickel, iron, manganese, carbon, German silver, copper, zinc, nickel. Brass is an alloy made up of copper and zinc. Bronze is an alloy made up of copper and tin. So all these are the examples of alloys. So alloys combination they'll ask in the exam, in the entrance exam. So please note it down. Next, now we are going to discuss questions based on this topic. Why does manganese plus 2 show maximum paramagnetic character amongst the bivalent ions of the first transition series? Because manganese plus 2 means, again you can see, go for oxidation state. Manganese plus 2, the oxygen state of manganese is what? So here, first manganese atomic number is 25. So it has argon 3d5 4s2. So after removing 2 electrons, it becomes manganese plus 2 becomes argon 3d5. 3d5 means stable. Due to half-filled d electrons, it is stable. So that's why it shows maximum paramagnetic character because it contains 5 unpaired electrons. How many unpaired electrons? Number of unpaired electrons is maximum 5 unpaired electrons because in 3d5 configuration, how the electrons are paired? No electrons are paired because first electron, second electron, third electron, fourth electron, and fifth electron. So since it has 5 unpaired electrons, it shows maximum paramagnetic character amongst the bivalent ions. Highest number of unpaired electrons in bivalent ions is only manganese because it has maximum 5 electrons, 5 unpaired electrons. That's why it shows maximum paramagnetic character because the magnetic moment of this is equal to root of 5 into 5 plus 2. 5 into 5 plus 2, it is equal to root 35. Root 35 is almost is 5.87 Bohr magneton greater than 5. So that's why it shows maximum paramagnetic character. So please copy down. Next continuation. Next question. Why are zinc plus 2 salts while white while Na plus 2 salts are blue? Because Zn plus 2 ions. Zn plus 2 means 3d10 configuration. No unpaired electrons. No unpaired electrons means it is colorless. That's why they are said to be white. So no unpaired electrons, that's why they are colorless. This is simple answer. So please copy down. Next question. Giving reasons indicate which one of the following would be colored. Simple it is. Which one of the following should be colored? Cu plus is colorless. VO2 plus. VO2 plus means vanadium in plus 2 state. So vanadium in plus 2 state, you can see 23. So it is expected to be colored because vanadium is argon 23. No, atomic number 23 means argon 4s2, that is 20, 3d3. 4s2, 3d3. So it is 2 plus means 2 electrons are removed. So it is 3d3 has unpaired. So it is colored. As it contains unpaired electrons, it is colored. Next we have scandium plus 3. Argon configuration only because all the 3 electrons are removed from scandium because scandium atomic number is 21. So it is colorless. No unpaired electrons because it is 3d0. Next we have Na plus 2, nickel plus 2. So atomic number of nickel is 28. So argon 3d 28 means 4s2, that is 20, and 3d8 actually. But Na plus 2 means this 4s2 will be going off, only 3d8. So it has unpaired electrons, so it is colored. It is again colored. So Na plus 2 is colored, VO plus 2 is colored, Cu plus is colorless, and scandium plus 3 is colorless. So we give reasons among which one of the following would be colored means only VO plus 2 is colored and nickel plus 2 is colored, and scandium and copper plus ions are colorless because they do not have unpaired electrons. As these have unpaired electrons, they are expected to be colored. Due to unpaired electrons, they are expected to be colored. So with the electronic configuration only, many questions you can answer in D block elements. That's why the electronic configuration of D and F block elements are most important. You have to learn the atomic numbers of D, 3D and 4D compulsorily so that you can answer the questions easily. Next question. The paramagnetic character in 3D transistor series elements increases up to manganese and then decreases. Explain why. Because pairing takes place, pairing of electrons in d orbitals takes place after 5. Example, you can say 3d6. What happens 3d6? Here it has even though 6 electrons, but still in the case of iron plus 2 example. So Fe plus 2, it has what configuration? 3d plus 2, 3d6. So as I told you, 1, 2, 3, 4, fifth electron, and sixth electron starts pairing up. So it has how many? 1, 2, 3, 4 unpaired electrons only. 4 unpaired electrons. So similarly, 3d7 will have 3 unpaired electrons. So 3d7, 3 unpaired electrons. 3d8, 2 unpaired electrons because it's taking place, pairing taking place. And 3d9, only 1 unpaired electron. And 3d10, 0. So that's why the paramagnetic character in 3D series elements increases up to manganese and then decreases. Because if you see for iron, mu is equal to root of 4 into 4 plus 6. 4 plus 2, sorry. So it becomes 24. Root 24 is nothing but approximately 3.87. So it is less than manganese because manganese is 4.87 or 4.90. So this is the reason. Next question. Why is the highest oxygen state of metal exhibited in its oxide or fluoride only? Because both are electronegative elements. Both are electronegative elements. That's why they can exhibit only fluoride or oxide only. Example, TiF4 and Mn2O7 as they are electronegative, they can form the higher. The oxygen state of titanium is highest, that is +4, and here it is +7. So as both are electronegative only, they can form like this. Next question. Calculate the spin only magnetic moment of M+2 ion. Z is equal to 27. It's very simple. Since Z is equal to 27, they have given luckily atomic number. Since Z is equal to 27, so actual M value for Z is argon, that is 3d18. Then we have 4s2. Then we have 3d 18 plus 20, so it is 3d7. And here 4s2, 2 electrons are removed. So M+2 means 2 electrons are removed. So it becomes argon 3d7. So 3d7 means it has how many valence electrons? 7 electrons. So how many unpaired? 3 unpaired electrons. 3 unpaired electrons. This you have to understand, because 7 means it has to be like this. Again, I'm showing because many students may not be understand. So first electron, second electron, third electron, fourth electron, fifth electron. So this is not here. Again, I'm drawing it. So M+2, it has first electron, second electron, third electron, fourth electron, fifth electron. Then sixth one will start pairing up. Seventh also will pair up. So it has how many unpaired? Now it has only 3 unpaired. You can just see here. It has how many unpaired? 3 unpaired. How many unpaired? It has 3 unpaired. So mu is equal to root of 3 into 3 plus 2. So 3 into 3 plus 2, it is equal to how much? 3 3s are 3 5 is 15. So root 15 is approximately 2.87. Sorry, 3.87, because root 4 square is 16. So it is 3.87 Bohr magneton is the answer. So spin only magnetic moment of M+2 ion in aqueous solution is 3.87 Bohr magneton. This type of questions are important for entrance exams. So all the questions which we are going to discuss now are important for entrance exams. So with this, I'm ending this session. So in the next session, we'll discuss more about D and F block elements. So please follow what we have discussed. All the points are very important. Thank you all.